All right. Awesome, y'all. Great. Does anybody remember what does the allosteric site do? What is its main role? Yes, so regulate and regulation is what I was going for, but how we talked about it, it's regulated by serving as an inhibitor spot. Yep. So one thing we didn't talk about in this class, because it's just not as relevant down the road, is you can also activate enzymes. So the allosteric site can also be where an activator would bind in order to turn an enzyme on. So we only talked about it in terms of inhibition. So on an exam, if I asked for the purpose, it would be to regulate the activity of the enzyme. But yes, Nathan, you're absolutely right. We talked about it for non-competitive inhibition. Speaking of which, good. So you definitely want to know competitive versus non-competitive inhibition. So this one is non-competitive because it binds to the allosteric site, which causes the shape of the enzyme to change, which warps that active site so the substrate can no longer bind. For competitive, that is when the inhibitor looks very much like the substrate, and so it binds to the active site and then prevents the reaction from happening. Huh. Well, that's because somehow two answers were allowed, and I didn't even think that was possible. It should be non-competitive. So I don't know how that's even possible. Okay, so it should be non-competitive. Let me make a note for that so we don't have this happen next semester. I didn't even know you could have two answers marked correctly. Okay, so competitive is where the substrate binds to the start over. The competitive inhibition is where the inhibitor looks like the substrate, so it binds to the active site, which physically blocks the substrate from binding. So remember, with competitive inhibition, there's a competition between the inhibitor and the substrate. They are competing for that key site, the active site. Okay. All right. Good. So remember, anabolic reactions build things. So maybe we're building a nucleic acid, we're building ATP, we're building, what did I put here? Proteins, okay? Anytime something is being made or created or built, that is anabolic, and that is going to require an input of energy. Reactions that require an input of energy are said to be endergonic, okay? So you'll notice the yellow one there was exergonic. Exergonic means that energy is leaving the reaction. And so that's associated with catabolic processes. So catabolic and exergonic go hand in hand. And then anabolic and endergonic, I'll put that in the chat just because it's kind of a weird word. Endergonic go hand in hand. So respiration is an example of a catabolic reaction, right? Because overall energy is being released as molecules are being broken down. Yes, good job. So remember, all of the reactions are metabolism, but we can break those down into catabolism or anabolism, also called catabolic and anabolic. So all the reactions that break things down are catabolic, all the reactions that build things are anabolic, but collectively, all the reactions are known as metabolism. All right, next up. Yes, so remember, this is where enzymes come into play. Because remember, before a reaction can happen, there must be enough energy put into the reaction, the activation energy. And so a lot of times that's going to be heat. So as heat is absorbed to reach this required amount, with increased heat comes increased speed of the molecules. So there'll be molecules here that are stable, then they're gaining a little bit of energy, energy, and eventually they're moving so fast that they break. And it's at that point when the molecules are moving so fast that they're bonds enough to break, when the substrate has now fallen apart so it can transition into the product. Okay, so that's why it's called the transition state. Now the substrate is weak enough to be broken down and converted into the product. So that is the transition state. All right, so proteins are the macromolecule that enzymes belong to. Okay, so most enzymes are proteins, and they act as catalysts, which speed up the rate of reactions. And they do that by decreasing the amount of activation energy needed to kickstart that reaction. Okay, so in order for some reactions to absorb enough activation energy to even get started can take days, weeks, months, centuries. And so we don't have that kind of time. And so enzymes decrease that activation energy, okay? And remember, enzymes are specific. They have a specific substrate, and therefore they catalyze a very specific reaction. It has just one job. It converts A to B. That's all it does. Same reaction over and over again. Good, good. Hopefully this stuff will stick now that I've asked almost every type of question I can think about activation energy and transition states. Awesome, good job. So it happens in the mitochondria. So the chloroplast is where photosynthesis would take place. The nucleus is where DNA replication and transcription take place. And then the cytosol, that's where respiration would happen mainly in prokaryotes. All right, question 9. All right. So in eukaryotes, glycolysis happens in the cytosol. It's the only step that happens outside of the mitochondria. And then the linking step and the Krebs cycle are going to happen in the mitochondrial matrix. And it's only the last step, oxidative phosphorylation, that happens in the membrane, because that's where the electron transport chain is and where ATP synthase is. And so remember, the last step is the electron transport chain. So during the linking step and during the Krebs cycle, the cell is still acquiring NADH and FADH2. So it's not quite ready to go to the electron transport chain, which is the only thing that's happening in the inner mitochondrial matrix. All right, next. All right. So ATP is made by oxidative phosphorylation in the very last step. That's when the electrons are being bounced down the electron transport chain, right? The protons are pumped against their gradient and they come back down using ATP synthase. That's only in the very last step. So during glycolysis and the Krebs cycle, ATP is actually made by stealing a phosphate group off of some other molecule in the cell and sticking it onto ADP. Because remember, ADP has 2 phosphates, and we need 3. So they get that third one by stealing it off some other molecule, sticking it onto ATP, and now we have 3. So that is called substrate level phosphorylation. Okay. So remember, FADH2 is only made during the Krebs cycle. So NADH is the stored energy made during glycolysis. ATP is the usable energy made during glycolysis. And pyruvate is also an energy yielding molecule because it's going to be broken down in the next step to harness more energy. So ATP, NADH, and pyruvate are all energy yielding molecules, but FADH2 is the stored energy only made during the Krebs cycle. All right, next question. All right, so one turn of the Krebs cycle is going to give 1 molecule of ATP, 3 NADH, and 1 FADH2. Okay, so 3 is the correct answer here. Had I asked how many molecules of NADH are made per molecule of glucose, then the answer would have been 6. Okay. 2 NADHs are made during glycolysis, and 4 NADHs aren't made at any point. So 2 would be for glycolysis, and 6 would be per molecule of glucose. Okay, hold on a second. Let me find the chat so I can. What if it asks me? Yeah, 2 turns of the Krebs cycle per molecule of glucose. Yep. All right, next question. Here we go. Very good. Very good. So the inner mitochondrial membrane would be for eukaryotes, but the electron transport chain is always embedded in a membrane. And so for prokaryotes, all they have that's a membrane is a plasma membrane. And so all the other steps of respiration would happen in the cytosol for prokaryotes. All right, question 14. Good. So during the linking step, two things happen. Pyruvate gets converted to acetyl-CoA, and NADH is released. Two of them specifically. Good job, y'all. Hey, wonderful job. So remember, with fermentation, they have glycolysis and some other reaction. So that other reaction doesn't yield any energy. So they only get their energy from glycolysis. That is it. Okay, so there's no electron transport chain, and there's no citric acid cycle or Krebs cycle, which is what I'll call it on y'all's exam, associated with fermentation. And respiration and fermentation are two different processes. So I'm glad that nobody picked that one. All right, number 16. Good job. So remember, cellular respiration is also called aerobic respiration. And so it's called aerobic because it needs oxygen. And it needs oxygen because it's the final electron acceptor. Because remember, during oxidative phosphorylation, that final step, remember NADH and FADH2 drop off their electrons and they play hot potato. They go from complex 1 to 2 to 3 to 4, and nobody wants them. They just keep passing them along. So finally, oxygen says, okay, I will accept them. And in doing so, becomes water. Okay, so the actual acceptor is going to be oxygen. All right, number 17. Good job. Does anybody remember how bacitracin works? So this, oh, there we go. Not quite. So there you go, David. It's the back off. Yeah, I said that during class. I'm glad you remember that. Yeah. So bacitracin prevents the NAG and NAM subunits, which build peptidoglycan. They prevent it from getting outside of the cell. So remember, peptidoglycan, the peptido means there's amino acids involved, peptido for protein. Glycan means there's carbs. So to build peptidoglycan, the two carbs are called NAG and NAM. And so they attach to each other. NAG, NAM, NAG, NAM, NAG, NAM. And then you'll see that over and over again. Okay, but in order to build that outside of the cell, right, because the cell wall is outside the cell, the NAG and NAM are made inside the cell where everything is made, and they export it. So they ship the NAG and NAM outside of the cell where it's then constructed. And so bacitracin says get back. It won't let the NAG and NAM out of the cell. So without the NAG and the NAM, the cell wall can't be built or completed. Okay, so the bacitracin, I think of the BAC as back, get back, you're not allowed out. Okay, so it prevents the cell wall from being built. It'll end up having holes and stuff in it because it's trapped inside. All right, next one. True or false? Good. What do quinolones target specifically? Which key player of DNA replication? Does anybody remember? Topoisomerase. Exactly. So I want to put in a little plug here for y'all's, depending on which class you're in, your project or your homework. We all have the same assignment this week. So I think a lot of people, because I've talked to quite a few people about this, I think everyone's making it a tiny bit harder than it needs to be. You don't need to be researching other drugs that currently exist. You can say, now pretend we hadn't talked about quinolones. So when you're trying to come up with your new drug or device, whatever approach you're taking, it can be as simple as saying, okay, I'm comfortable with DNA replication, so I'm going to pick that process to target. All right, who are my key players? There's 7 of them. All right, I am going to target topoisomerase because without it, right, the DNA is going to get really, really coiled, it's going to get brittle, and it's going to break. And so you literally just pick a target, topoisomerase, and you say, my antibiotic prevents it from doing its job. So that's as easy as the mechanism part. You pick your target. And then in your infographic, you say, a key part of DNA replication is topoisomerase, which relieves supercoiling. My drug, enter name here, binds to topoisomerase, so it can't relieve supercoiling. This causes supercoiling, and the DNA will break. Bam, done. End of story. That's it. Okay, so now you can't pick topoisomerase because we've talked about it in class, but there are several other key players that you could target. And by targeting that key player, it can't do its job. So you have to figure out, well, if I target the single-stranded binding proteins, what's the consequence? What does the single-stranded binding protein do? So therefore, what will not happen if it's unavailable? Okay? So that's why I said it should only take an hour or two, because you're not coming up with some brand new mechanism out of the blue, right? You're just not using one of the 14 that we talked about in class. Everything else, all the other key players or key structures, they're all up for grabs, okay? But you don't have to be super detailed on exactly how you're binding topoisomerase. You're just telling me that you are. I'm going to bind it, prevent it from doing its job. Or my antimicrobial is going to bind to RNA. So therefore, now the ribosome can't access it because my antimicrobial is acting like a roadblock on that messenger RNA. Cool. Done. Okay? So if you think you're overanalyzing it, stop that. Okay? It's not meant to be that tricky. Okay? All right. Last question. True or false? Good. So bacteriostatic agents will prevent the bacteria from growing. They stay alive, but they cannot replicate. They can't make more. Therefore, they kind of just like die of old age. Okay. Bactericidal agents will kill bacteria. All right, so that was our last question. Are there any lingering questions based off the content we just covered? Okay. All right, so I've got an antimicrobials Kahoot. Do we want to play that, or do we want to switch gears to more of like a handout situation? Yes, Nathan. Yes, it does. The electron transport chain occurs in the inner mitochondrial membrane. I've got to vote for each one. We're still tied. We're still tied. So far, Nathan's okay. Now we're starting to lean towards the Kahoot. Okay, so we're gonna go ahead and do that one. Yes, Brittany, absolutely. Only what we've covered in that antimicrobial drug PowerPoint. Okay, so we're gonna leave this one, and I've got another one, but nothing in. What do you mean by DEPT? I'm gonna get this one up and going. So you'll need to know it as in depth as I talked about it in class. So the names, the mechanisms, that sort of thing. But no, you shouldn't have to go do any like extra research or anything on it. These Kahoots, yes, I will be posting them later. Yep. And that's kind of why I'm glad we're going through this one now, just because it gives people extra time to go through them and review them. All right, so here's your new Kahoot. So tomorrow we'll do the little handout that we were going to do tonight, and some practice exam questions, and then I'll have a Kahoot ready in case we have some more time. Oh no, still crying. I have faith in you. I bet you're going to do awesome. If you need to talk, let me know. All right, where are we at? We're at 12. I think we had 13 or 14 last time. So I'm going to give, and I saw a couple people enter. So let me wait just a few more seconds here. I think this one's only, crud, how many questions was it? I think it's like 11 or 12, so it won't take a ton of time. All right, I haven't seen anybody else join. Oh, there we go. Yes. Yes, Nathan. All right, so we're going to go ahead and start. I believe it's an unlocked game, so you can always join later if you need to. The pin will be at the bottom of the screen if you want to join late. Yes, so our sulfa drugs target folic acid synthesis. And the other three target translation. Remember, that's also called protein synthesis. Now, I'm not going to remind you of what each of those do because we're going to have questions on those here coming up. But the sulfa drugs use competitive inhibition to prevent folic acid from being made, which is essential to many key processes in bacteria. Us too, but we get our folic acid from our diet, so we don't have the enzymes that are being targeted. So it's really actually a very safe drug for us. Okay. Good. So penicillin and cephalosporins, those are going to be the beta-lactams. Okay, so remember, those are going to block cell wall synthesis by competing with the enzyme that cross-links those glycan chains. Okay, so penicillin and cephalosporins are both beta-lactams. And then bacitracin was the one we just talked about that says get back, that doesn't let the NAG and NAM out of the cell. So tetracycline, that was the one that in class that I talked about. It was a really broad spectrum antibiotic. It targets the gram-negatives, the gram-positives, and then chlamydias and rickettsias, which just have unique life cycles that we'll deal with later. But tetracyclines, because it shuts down translation, it's able to be effective against most organisms. I like seeing how quickly y'all are answering this question. Yes, good job. You did not fall for my trick. So why is the Golgi not a target of many antimicrobials? Because we have those too, right? And it's all about selective toxicity. Okay, good old Elric talked about selective toxicity. And we want to develop or find antibiotics and things that are going to harm the target, not the host. Okay, so good job on that one. Good. Rifamycin binds to RNA polymerase, and it completely prevents transcription from even happening. RNA polymerase cannot bind to the DNA. It cannot read that template strand to create our messenger RNA. So good. So remember, fluoroquinolones were in the last Kahoot that's targeting the topoisomerase. So it's targeting DNA replication. Cephalosporin, that's one of our beta-lactams, so that was targeting the cell wall, and aminoglycosides target translation. So, one approach to studying these is to make sure you first know the big structure or process it's associated with. Because if you knew that the fluoroquinolones target DNA, aminoglycosides target proteins, and cephalosporins target the cell wall, well, that leaves rifamycin by default to target transcription. So these target 4 very different structures and processes. That should say translation, sorry, y'all. All right, so tetracycline was the other drug that is going to target translation. The other 2 don't have anything to do with translation. So daptomycin is for the plasma membrane, and the sulfa drugs are for folic acid synthesis. Okay, so tetracycline or chloramphenicol, totally rough, is going to be preventing peptide bond formation. And we're going to get to tetracycline later, so I'm going to leave that one in my back pocket. Hey, good job. And so remember that that enzyme is called penicillinase. So that enzyme specifically targets penicillin, but more specifically, it targets the beta-lactam ring. Okay, that's why they're called beta-lactams, penicillin and cephalosporin. And it's that beta-lactam ring that gives it its antimicrobial properties. Okay, so a lot of organisms have evolved making penicillin not quite, have evolved to have penicillinase, making penicillin not quite as effective as it used to be. Okay. Oh, we already did this one, I'm sorry. Pick yellow, pick gold. So in bacteria, some of their topoisomerases are called gyrases. But on your exam, it'll be called a topoisomerase. So let me write that down. What question is this? Number 7. Okay. So on your exam, that would say DNA topoisomerase. I just forgot to update this one. All right. So good job. The majority were on the 2 that target translation. So that's awesome. So again, sulfa drugs are folic acid synthesis. Bacitracin is the cell wall, preventing NAG and NAM from getting out. So erythromycin is going to prevent the initiation complex from forming. It prevents the ribosome from joining the team. And then tetracycline physically blocks part of the tRNA binding site. So it's going to prevent that tRNA from gaining access to the ribosome. So no proteins are going to be made. Exactly. That's how I actually remember it. Yeah, so probably why half of y'all just missed this one is because I just misspoke. Erythromycin prevents the ribosome from moving along the messenger RNA, so I'm very sorry about that. Oxazolidinones prevent the initiation complex from forming. Erythromycin prevents translocation of the ribosome. So I'm sorry if I swayed some of y'all's choices. My apologies. Good. What do polymyxins target? The membrane, exactly. Gram-positive or gram-negative organisms? Good, 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 good. Okay. Gram-negative. All right, last question. You gotta chill out, bud. Good. So I noticed not so many people answered this question. So here's what I want you to think about. So say you see a question like this and you're like, Chelsea, that exact wording is not on your PowerPoint. That exact wording, was not in anything that you said. True. How can you still answer it? Again, knowing what the others do, right? Process of elimination. So if we're dealing with peptidoglycan, we're dealing with the cell wall. Well, chloramphenicol deals with translation. Quinolones deal with DNA. Rifamycin deals with transcription. So the only one left is cephalosporins. Those are our beta-lactams, okay? It's the only option on the screen that even deals with the cell wall, okay? So just make sure, again, that you know the big overall target of each one because it can help you eliminate answers. Now, I know you only had 20 seconds, so maybe not enough time to go through all of that. But on the exam, that's kind of an approach you would want to take. All right, that was the last one. So these will be posted a little bit later. So what we're going to do now, hold on, let me find where I just put it, is metabolism. I'm trying to get this to, there you go, be one page. Metabolism tends to be where people struggle the most on this exam. That and the antimicrobials, okay? But you've got all the information for the antimicrobials. That one's really just giving yourself time to memorize it. And I guess you could argue that with respiration as well. But for those of you that are more table people than maybe graphic organizers, let's just go ahead and fill out this table really quickly. And then I will take any questions that y'all have because that's really mainly what I've got for tonight. So on your own, go ahead and create this little box. And then fill out the name of each step for respiration. So that includes the linking step, but try to write out its actual name if you remember what it is. All right, let's see. I might have to move this to my smaller screen so I can actually write on it. Okay, hold on. Just stop sharing my screen real quick. And let me share this other screen. Okay. All right, let me move this over here. Let me move y'all to my other screen so I can see you. Okay, there we go. All right, I'm gonna turn my video off so y'all don't have to see me up close and personal. All right, so here we go. So our first step, what is it? Can somebody tell me what our first step of respiration is? Yes, glycolysis. Good. So I'm gonna write glyco as well because I just don't have a lot of room. All right, does anybody remember what our linking step is called? Hey, yes, good. So it's pyruvate, which was just made at the end of glycolysis. And it's in this step, pyruvate is going to be oxidized. So pyruvate oxidation, that's our linking step. And then our next step is going to be the Krebs cycle. And the last step is going to be oxidative phosphorylation. So I'm just going to abbreviate that OPP. All right, so we got to always know what goes in and what comes out. Now remember, for me, I am not concerned about carbon dioxide in this process. I'm concerned about energy products. So I know carbon dioxide gets released along the way and it goes off into the atmosphere, which is fabulous. But I'm not going to be testing you on anything to do with carbon dioxide. Bigger fish to fry. All right, so what is our starting molecule? What is our input for glycolysis? Yes, glucose. And what are our three outputs? What are the three products of glycolysis? All right, good, Nelly. 2 ATP. That's our usable energy. What else are we going to make? Good. 2 NADHs. That's our stored energy. And then we're one more. 2 of something else. Nice, y'all. 2 pyruvate. We're going to come back to the fun facts later. I want to make sure that you see how everything is connected. Hey, move, buddy. Stop. Why do you yell like that? Just move. Good grief. Gives me a heart attack. He was a bait dog when he was younger, and so his natural reaction is to just scream his head off if he doesn't like something. So I'm sorry y'all had to hear that. Goodness. Whew. Okay, so our outputs are going to be inputs to the next step, at least some of them. Okay, that's how this works. So our ATP is going to be used immediately. NADH is our stored energy. And so those are going to go and be dropped off at the electron transport chain. So the output that we're still going to be dealing with is our pyruvate. So the pyruvate is going to be our input. Does anybody remember what is made? What is made at the end of the linking step? Stay out there, Kane. Little screamer. Nope, stay out there. Little booger. All right, good. I see both the answers I'm looking for. Acetyl-CoA, which I'm going to abbreviate as just ACA, and then NADH. Now they're made in a 1:1 ratio. For every 1 pyruvate, they get 1 acetyl-CoA and 1 NADH. So because 2 pyruvates go in, we're going to get 2 of each of these coming out. So we know that NADH is going to go off to the electron transport chain. So what must our input be for the Krebs cycle? Good old acetyl-CoA. That's the whole point of the linking step. Pyruvate alone cannot go into the Krebs cycle. And so we need that linking step to generate the acetyl-CoA, which can go into the Krebs cycle. Okay? So acetyl-CoA is going to go in. And what are going to be our 3 energy yielding products per 1 acetyl-CoA? Because remember, only 1 can go in at a time. So somebody tell me what we're going to get. Good. So we're going to get 3 molecules of stored energy for NADH. We're going to get 1 molecule of usable ATP. And then who's left? Good. 1 molecule of FADH2. So at this point, we look at our outputs and say, all right, what's happening here? So the ATP can be used right away, and we've got stored energy. Okay, lots of NADH and some FADH2. Now remember, y'all, this is 1 turn of the Krebs cycle. How many acetyl-CoAs do we actually have right now? Right? 2. So I'm going to write a ×2 right here because that means we need 2 turns of the Krebs cycle. So then you would take these numbers and multiply them by 2 if I asked for how many of these are going to be made per molecule of glucose. Per molecule of glucose means we're starting from the top. Well, 1 glucose made 2 pyruvates. That made 2 acetyl-CoAs, so that's 2 turns of the Krebs cycle. So we get 6 NADH, 2 ATP, and 2 FADH2. All right, now which of our outputs are going to go in to oxidative phosphorylation? Well, not ATP, right? Because that can be used immediately. So our NADHs, all of them from all the steps, all the NADHs and FADH2s are going to be dropped off at the electron transport chain. And again, they're going to bounce down the chain and they are going to end up with lots of ATP being made. Lots of it. Normally it's like 30 to 32 molecules total are made. Okay, so that's what's going in. And remember, y'all, for the NADH from glycolysis, from pyruvate oxidation, from the Krebs cycle, they're all going to end up at the electron transport chain. So down here at oxidative phosphorylation. All right, so we've only got 3 minutes, so I'm going to go ahead and remind you of some fun facts for each of these. So glycolysis is going to happen in the cytosol for both prokaryotes and eukaryotes. This is the step that can happen with or without oxygen. And ATP is made via substrate level phosphorylation. And I abbreviate that SLP because it's just a lot to write. Substrate level phosphorylation is how we made those 2 molecules of ATP. All right. So with pyruvate oxidation, you're going to remember that this is going to be happening in the cytosol of prokaryotes and in the mitochondrial matrix for our eukaryotes. And that's really the only thing you've got to remember for pyruvate oxidation. Now for the Krebs cycle, doesn't it make sense that the Krebs cycle should be at the same place as the linking step? Because the linking step made the starting molecule for the Krebs cycle. So wouldn't it make sense that the starting molecule is made in the same place as the cycle itself? So we're still here in the cytosol and in the mitochondria. So remember, for both of these, at this point, oxygen is required. And the only other thing I stressed about the Krebs cycle is that the last molecule made in the Krebs cycle is going to be the one that interacts with each acetyl-CoA as it comes into the cycle. And that molecule is oxaloacetate. Oxaloacetate. So that's the last molecule made in the cycle, but it reacts with the incoming acetyl-CoA to kickstart another turn of the Krebs cycle. And then with oxidative phosphorylation, this is either in the plasma membrane or in the inner mitochondrial membrane. And yeah, so normally the ATP made during oxidative phosphorylation, it's roughly like 30 to 32 normally, sometimes up to upwards of like 34. Okay, because overall it tends to make approximately 38 ATPs from the very beginning, including glycolysis and pyruvate oxidation and all of those. So sorry, I think earlier I said 30 to 32. It's normally about 32 to 34. Okay, so with oxidative phosphorylation, here we're seeing tons of redox reactions. And here is also where the proton motive force, those protons getting forced against their gradient to cross the membrane. And here is also where ATP synthase is located. All right, y'all, it is 7:01. I apologize for going a minute over. That is it for tonight. Tomorrow we'll do a little bit more of like practice questions and handout type things, and I'll try and have a Kahoot ready if I can think of enough other questions. All right, good. I'm glad that it was helpful. I'm going to stop recording now. People don't need to hear anymore.